I'm fine, Alice, and you?
I'm good. Thanks for asking me, Petara. So I hope you are always in a good condition, guys. Okay, so are you ready to study now?
Inshallah.
Okay, you must ready to study right now. Okay. Before we start our lesson today, it will be better if we are praying first. So please, one of you can lead the prayer. Who is the leader of this class?
Putri.
Okay, please Putri lead the prayer.
Alright guys, before we start our lesson, let's pray together. Praise begin. Finish.
Thank you, Putri. Now let me check your attendance first. If I call your name, please raise your hand and say present. The first one, Sania,
Present, ma'am.
and then Putri,
Present.
Petara.
Present.
Okay, everyone is here. I hope everyone is excited for today's lesson because our discussion today is very interesting. And so guys, because I know that physics is not easy, please believe in yourself because you can if you think that you can. Remember that who is serious will surely get success. This also applies when you study physics. When you study carefully, seriously, you will be able to achieve the best result. Okay, so today we will continue our discussion to the next chapter regarding to the magnetic field. But before that, I have some question for you guys. In our everyday life, you must be familiar with magnets. What do you think when you hear the word of magnets? Sania?
Can pull some object maybe?
Okay. And then Putri?
South and north.
Petara? Okay. We often think that when we hear the word of magnet, it is always related to the objects that attract or repel each other. And then magnets are very useful for our life, such as attracting the objects that fall in places that we cannot reach with our hand. And then in addition, many tools around us use this concept of magnets. For example, the compass, and then the telephones, power generators, and many more. Besides magnets, we also often hear about the magnetic fields, which we discuss today. And in the end of this chapter, you must be able to achieve several learning objectives, include identifying the definition of the magnetic field, and then identifying the magnetic induction around the straight wires, also around the circular wires, and then explaining about the magnetic field around the solenoids and also the toroids. And you must conducting the experiment regarding to the magnetic induction on the solenoids, and you must presenting your result from your experiment. Okay, let's start our lesson because I know you guys cannot wait to study physics right now. Okay, wait a minute. Okay. Okay, as I said before, today we are going to study about the magnetic field. Vetara, what's your opinion about the magnetic field?
Magnetic field is area around magnet.
Okay. Any other opinion? No? So the magnetic field consists of two words, magnet and field. Okay, magnetic field consists of two words, magnet and field. The fields mean the area. Sorry. So we can say that the magnetic field is the area around the magnet that's still affected by the magnetic force. Okay, there is some problem with my slide. Okay, let's continue. So the magnetic fields can be generated from the magnet, and the direction of the magnetic field is described with the lines of the magnetic force. The direction is from the North Pole to the South Pole. So if I have the magnet, there is the North Pole and this is the South Pole. So the magnetic field will be like this. Okay, this is the magnetic field. Apart from being generated from the magnets, the magnetic fields also can be generated from the electric currents that we call as the magnetic induction. But before we learn more about the magnetic induction, we will learn about the magnetic properties of the materials and the Oersted experiment. Okay, the first one we will learn about the magnetic properties of the materials. So, as you can see in my slide, the magnetic properties of materials are divided into three types: ferromagnetic materials, paramagnetic materials, and the diamagnetic materials. The first one is the ferromagnetic materials. There are the materials that very easy to affected by the magnetic fields and can be used as the permanent magnet. For example, the iron and then steel, nickel and cobalt. And the second one is the paramagnetic materials. That are the materials that not easy affected by the magnetic fields. For example, the aluminum and then the platinum. And the last one is the diamagnetic materials. That are the materials that cannot be affected by the magnetic field. So the diamagnetic materials cannot be used as the magnet. For example, the gold and the silver. Okay. Is it clear, guys? Do you have any questions? No? If there are no questions, let's continue our discussion about the Oersted experiment. So in this topic, we will learn about how and what is the results from the Oersted experiment. So in 1819, Hans Christian Oersted did an experiment. On this experiment, Oersted placed a compass needle near the wire that not carrying an electric current. And also, Oersted placed a compass needle near the wire that carrying an electric current. And from this experiment, Oersted saw that when the compass needle placed near the wire that not carrying an electric current, the compass needle would not deviate or change position. But when you can show this picture. When the compass needle placed near the wire that carrying electric current, the compass needle will deviate from the original position. And from this experiment, Oersted conclude that around the current carrying wire, there is the magnetic field, and the direction of the magnetic field can be described using our right hand rule, where our thumb shows the direction of the electric current and our grip shows the direction of the magnetic field. Okay. Here I have an example for you guys. So, okay. I have the current carrying wire where the current is up and there is the point P that to the left of the wire and point Q to the right of the wire. Okay, if we use our right hand rule, it means that our thumb shows the direction of the electric current. So our thumb is pointing up, and the magnetic field around the wire will be rotated like this. Please try with your right hand, please. Okay, great. So it means that the direction of the magnetic field will enter the field through point Q and exit from the field through point P. Or in other words, the magnetic field will, at point Q, will into the page, and at point B, the magnetic field will out of the page. So we can symbolize the direction of the magnetic field. If the field is into the page, we can symbolize it with cross sign. And if the magnetic field out of the page, we can symbolize it with dot sign like this. Okay, now how if the electric current is to the right or to the left side? As we can see here, if I have the current carrying wire and the electric current is to the right, maybe Putri,
Yeah.
can you determine the direction of the magnetic field?
This.
Okay.
But
If there is point P and there is point Q, at point P, where's the direction?
the current will go outside.
Okay,
to point
outside.
B, and then it will enter to point Q.
Okay, that's right. Give applause to Putri, please. Okay, next. Any question from you guys? Okay. Let's continue our materials to the magnetic induction, or we know as the magnetic field that generate from the electric current. So in this subchapter, we will learn about the magnetic induction around the strike wires and then the circular wires, solenoids, and also the toroids. The first one is the magnetic induction around the strike wires. So the first one, okay. The first one about the magnetic induction around the strike wire. So if I have the strike wire, and this is the infinite strike wire, it means that the length of the wire is very long. So if there is an electric current and there is point X, which a distance A from the wire, we can formulate the magnetic induction at point X by B is equal to mu 0 times I divided by 2 phi A, where B is the magnetic induction in Webers per ampere meter or Tesla, and then mu 0 is the permeability of the vacuum, I is the electric current, and A is the distance between the point X and the wire. Okay. Meanwhile, for the finite strike wires, here I have the strike wire with length L, and then this is the electric current, and there is the point X with the distance A from the wire, and this is theta 1 and theta 2. The magnetic induction at point X can be formulated by B is equal to mu 0 times I divided by 2 P A, and then times cosine theta 1 plus cosine theta 2, like this. And then there is an example where there is a wire carrying an electric current with I is equal to 2 amperes, and as shown in this picture, and we need to determine the magnitude and the direction of the magnetic induction at point P and point Q. So we have determined the direction and the magnitude of the magnetic fields at point P and point Q. Before we calculate the magnitude of these 2 points, the first step that we have to do is determine the direction of the magnetic field. So if we use our right hand rule, our thumb is pointing to the up, and the magnetic field will into the page at point Q and out of the page at point P. And we can determine the magnitude of the magnetic field use this equation. So at point P, the magnitude of the magnetic induction is formulated by B is equal to mu 0 times I divided by 2 PA. And we input the known values and the coefficients, where mu 0 is 4 pi times 10 to the power of minus 7 times I is the electric current, and this is equal to 2 amperes. Okay, this is 2 and divided by 2 pi times A is the distance between point P and the wire. So this is 2 meters. And so we get the magnitude of the magnetic induction at point P is equal to the 2 times 10 to the power of minus 7 Tesla. And the direction is out of the page. Okay, it's the same with the point Q. Anyone will want to prove this equation, this example? Maybe Petara, please find the magnetic induction at point Q. Okay. Okay, and the direction? Okay, thank you, Petara. You can back to your seat. Okay, guys, let's look at the whiteboard. So, at point Q, we use the same formula with the point P. So, the magnetic induction at point Q formulated by mu0 times I divided by 2P times A. So, input the known values and the coefficient, and we get the magnitude of the magnetic induction at point Q is equal to 4 times 10 to the power of minus 7 Tesla, and the direction is into the page. So this is the right answer. Please give applause to Petara. Okay. The second one is the magnetic induction around the circular wires. Magnetic induction around the circular wires. Okay, for example, if there is the circular wires with radius A, and this is the point O at the center of the wire, and there is point X out of the wire, and this is theta. So we can formulate the magnitude of the magnetic induction at point O. B at point O is equal to mu0 times I divided by 2A, and for the point X, Px can be formulated by mu0 times I divided by 2A times sine theta q, where the P is the magnetic induction, mu0 is the permeability of the vacuum, I is the electric current around the circular wires, and A is the radius of the circular wires. Do you understand, guys?
Yes, ma'am.
Okay. The next one is the magnetic induction on the solenoids. Before that, do you know what is the solenoid? Petara, do you know what is the solenoid? No?
It's not oil.
Okay, Sania?
It's not oil.
Okay, so the solenoid is the wire that form is like a spiral, right? Okay, so Sania is right. Magnetic induction on solenoids. So the solenoids is like this, and the magnetic induction at the center of the solenoid can be formulated by B is equal to mu0 times I times N divided by L, and at the ends of the solenoids can be formulated by B is equal to mu0 times I times N divided by 2L, where L is the length of the solenoid and N is the number of turns of the wire. induction on toroids. So the toroids are the solenoids that we form in a circle, or in other words, toroid is the circular solenoids. The form of the solenoids is like this. I'm sorry. The form of the solenoid is like this. So this is the circular solenoid, and we can formulate the magnitude of the magnetic induction at the center of the toroids with P is equal to mu 0 times times N divided by 2 PR. So if we look at this equation is same with the equation on solenoid on the center of the solenoid. But the L is the circumference from the wire, so this is 2 VR. I think that are the simple concept of the magnetic field. If you doesn't understand about it, maybe we can talk more about it in another occasion, or maybe you can learn with yourself on home to improve your understanding. And now let's continue our class with the interesting activity. So we will do the experiment according to the magnetic fields, especially the magnetic fields on the solenoids. Okay, so guys, I will ask you to do an experiment in groups, and I will divide you into two groups. Maybe group 1 consists of Petara, and group 2 consists of Sanya and Putri. Okay. So, if there is enough time, please do experiment and then collect the data, also the documentation, and you have to analyze your data, and please present in the front of the class. But if there is not enough time, you can present your results for the next meeting. However, before you do the experiment, I will show you how to conduct the experiment. So the first one that we have to do is prepare the tools and the materials. Okay, the tools and the materials that we need in this experiment are relatively easy to find around us. The first one, we have one battery with voltage of 1.5 volts, and then we need 1 meters of the copper cable as the conductor of the electric current, and this battery is for the source of the electric current, and we need 1 iron nail with length 7 centimeters long for the ferromagnetic materials, And we also need the cutter or sizer to peel the cable, and then the tape to attach the ends of the copper wire to the poles of the battery. And the last one, we need some paper clips to prove whether our experiment is successful or not. So let's start our experiment. If the tools and materials that we need are ready, the next step is to peel the cable using our cutter. So if we peel the cable, we will get the copper wire like this. Okay. And the next step is wrap the copper wire around the nail with 10 turns of the wire. So you have to do like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Like this. Can you see it, guys?
Yes, miss.
Okay, after that, attach the two ends of the copper wire to the two poles of the battery using the tape. So the function from this tape is to avoid the heat from the copper wire and the battery, or you can also use the tissue or the paper to avoid the heat. Okay. Just do like this.
You will help me.
Yes, Petara, please come here.
Help me. Yes.
Okay, thank you, Petara. Okay, please. Okay, like this. Can you see it, Sania?
Yeah.
Okay. After we attach the two ends of the copper wire, and then wait a few moments and hold the nail close to the paper clips and observe what happened with the paper clips. Okay. As we can see, there are some paper clips that are attracted to the nail, and it means that our experiment is successful. And for 10 turns of the copper wire, there are two paper clips, only two paper clips that attracted to the nail. And we can write down the result into the observation table data on the worksheet that I will share with you. And then for the second data, we need 20 turns of the copper wire. So because here we have 10 turns of the copper wire, so we need to add more turns. Sania, maybe you can help me? Okay, please add 10 more turns.
1, 2, 3, 4, 5, 6, 7, 8,
Wait.
9, and 10.
Okay, thank you, Sania. Okay, after that, just like before, we attach the two ends of the copper wire to the battery using the tape. You Okay, wait a few moments and hold the nail close to the paper clips and observe again what happens with the paper clips. So, as we can see, the number of the paper clips that attracted to the nail is more than before. It is right?
Yeah.
Yeah. So we calculate the number of the paper clips. So here 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have 9 paper clips on the nail. And write down to the table. And for the last one, we need 30 turns of the wire. Okay, 30. Okay, like this, guys. And after that, we attach again to the battery using this tape. Okay, Fetara, please hold the nails close to the paper clips and observe what happens with the paper clips. Okay, please show to your friends. So guys, if we look at these paper clips, we know that the number of the paper clips that attracted to the nails is more than before. So here, okay, thank you Fetara, you can back to your seat. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. With 30 turns of the copper wire, we get 10 paper clips that attracted to the nails. So this is the experiment that you have to do, and please don't forget to write down the results on the worksheet that I will share with you, and then please collect the data and analyze. After that, please present in front of the class, and maybe one member of your group can come here. This is for group 1. Yes, and this is for group 2. Okay, please conduct the experiment with your groups for 10 minutes. Start now. Okay, do you have a problem, Petara? Sorry guys. This is for seminar and okay guys, I think the time to do this experiment is up. Do you have finished your worksheet? Okay. Great. Group 1, have you finished your worksheet?
Already.
Group 2?
Yes, ma'am.
Okay guys, because you have to do the experiment, and now please present your results from the experiment. Maybe from anyone want to come to the front of the class? Group 2, please. Please present the conclusion from your experiment.
Okay, after we conduct the experiment, we got the data that when 10 turn off the copper wire, the number of the paper clips that attracted to the nail are 3 paper clips. And for 20 turn, there are 5 paper clips, and the rest with 30 turn, there are 8 paper clips on the nail. So, we can conclude that when the electric current flows through the nail, there is the magnetic field and cause the nail can attract the paper clips. And then, based on our result, the more turn on the wire, the more paper clips are attracted to the nail. It turns out that the stronger the magnetic induction in generated.
Okay, please give applause to Sania and Group 1. Okay, thank you, Sania.
Okay.
So guys, I think the time is up, and maybe Group 1 can present your results for the next meeting.
Okay, yes.
And I will add more information. So from this experiment, we know that when the electric current flows through the wire, there is a magnetic field and cause the nail can attract the paper clips, and more than turns of the copper wire will generate the stronger magnetic field and cause the nail can attract more paper clips. And this is according to the magnetic induction that we have learned before, where B is equal to mu0 times I times N divided by L, where B is directly proportional with N. Okay, so I think enough for today. But before we go, what can conclude what we have learned today? Okay, so today we have learned about many things, starting from the definition of the magnetic field, that are the area around the magnet that is still affected by the magnetic force, and then we also study about the magnetic induction around the strike wires and then circular wires, solenoids, and also toroids. And we have conducted this experiment regarding to the magnetic fields, especially the magnetic fields on the solenoids. And I think enough. Any question, guys? No? So we will stop here. Please don't forget to review again what we have learned today. And before we end this class, let's say Alhamdulillah together. Alhamdulillahirabbil alamin. Thanks for your great attention, guys. See you next meeting. Wassalamualaikum warahmatullahi wabarakatuh. Yes. Okay, see you guys.